And so to the speakers, I'll let you know when you have 5 minutes remaining. So after 25 minutes is gone. Okay, let's get started then. So our first speaker is Gabriel Haeser from São Paulo in Brazil. Gabriel, are you here?
Yeah, I'm here.
Okay, I see. Okay, and he's going to tell us about constraint qualifications for conic programming. So the floor is yours.
Okay, thank you, Matthew. Thanks also to Vera for inviting me to this nice conference. So I'll talk about this joint work with Roberto Andriani from the University of Campinas, Leo Mito, which is my PhD student in São Paulo, and Hector Ramirez from the University of Chile. So in this work, we are interested in constraint qualifications for these two types of conic optimization problems. So it's the nonlinear second order con programming and the nonlinear semi-definite programming problem. So here you have a constraint function G from Rn to Rm. These are all smooth problems, C1 functions. And the constraint, instead of being G belonging to Rm plus, which would be the standard nonlinear programming problem, we replace the conic constraint by the inclusion to this second order con. So this is the so-called ice cream cone or Lorentz cone. So instead of all components being non-negative, we have to choose one special component, which we call the 0, 1, and the remaining vector we call z hat. And the constraint is that the first component is larger than or equal to the norm of the remaining vector of components. Okay, so this is the problem. And in terms of the derivative operator, you have the transpose Jacobian, which you evaluate at a vector mu, and it's simply the linear combination of the gradients. So in terms of derivative, this is exactly the same as a nonlinear programming problem. So it's a very similar structure. For SDP, the things are a little bit different, but not that much. The constraint here, it takes values, you take a x in Rn, and you associate a symmetric M times M matrix. And the constraint is that this matrix is positive semi-definite. And here also the derivative operator, which is the adjoint transformation here, you evaluate it at a symmetric matrix omega, and what you get is also a linear combination of the gradients of each component of this matrix G. So in terms of derivatives, this is quite similar to nonlinear programming, and we want to discuss first order optimality conditions of these problems. So under a constraint qualification at a local minimizer, we can show the existence of a Lagrange multiplier, which is a vector in the case of second order con programming, or a symmetric matrix in case of SDP, such that this usual gradient of the Lagrangian is 0, which is exactly the same as NLP, and also this complementarity constraint. For SDP, it's exactly the same, linear combination of the gradients and complementarity. Here, this is the standard inner product for symmetric matrix space, which is the one that gives rise to the Frobenius norm. But it's exactly the same as nonlinear programming also. The difference here is that we have dual feasibility here. The multiplier must be inside the cone, and a primal feasibility, also for the SDP. So if this were a nonlinear programming problem, if we had the cone Rm plus, then this complementarity could be decomposed by components. Gi, mu I would be equal to 0. And then in some sense, a nonlinear programming problem is very easy because it can be decomposed by components. In some sense, we can say that nonlinear programming constraints are also one-dimensional. We can replace these M constraints by this one constraint by M individual constraints. And so this type of problems are more challenging because we have these different types of constraints which cannot be separated, such as in nonlinear programming problem. We will consider a simpler case, which is when G of X bar is 0, or here when the matrix is 0, which is the hardest case typically. But for us, which we come from nonlinear programming, it's simpler because this complementarity says nothing. It's automatically satisfied. So at least the expressions are easier to, are more similar to what we get in nonlinear programming. Otherwise, this complementarity gets mixed up with this condition and we get a little bit confused. Okay, so what's the standard constraint qualification for this type of problems? It's the so-called non-degeneracy condition, also called transversality. And when the constraints are at 0, this is simply the gradients of each component of these constraints are linearly independent. It's exactly what you would have if this were a nonlinear programming problem. And also for SDP, it's the same. The gradient of the components. Remember that the constraint G, it's a symmetric matrix. So we consider only the upper half part of the matrix. And we ask that all these gradients must be linearly independent. So this is the very standard formulation of LICQ for these conic constraints. So one thing that catches our attention is that for SDP, when you have a diagonal case, which is a very simple case, because if you have a nonlinear programming problem, you can, it's very natural to consider it as an SDP problem, putting the constraint in the diagonal. But in this case, this non-degeneracy condition never holds, because you have a constraint which is, the gradient is 0, so it's not linearly independent. So this is weird for us coming from nonlinear programming. And but what we want to do in this paper is to develop new constraint qualifications. For nonlinear programming, we know the constant rank constraint qualification from Janin, 84. It asks, instead of asking full rank of this set of gradients, it asks for constant rank. That is, the rank may not be full, it may be non-full rank, but it must be the same in a whole neighborhood of the given point. And so you could try a naive approach and say, okay, so maybe constant rank for SOCP is simply asking the same thing, constant rank of these gradients or constant rank of these gradients. But then you see that this cannot be the case, because for these conic problems, when you have a linear problem, you have duality gap. So there are linear problems which would fulfill this naive constant rank constraint qualification, but there is no Lagrange multipliers. So we have a previous paper which defines a naive constant rank condition, but it's defined in such a way that when we look at these conic problems, only the simple case when the problems are in fact one-dimensional, when each block of constraints are one-dimensional, and then we can mimic the techniques used in nonlinear programming to define these naive constant rank conditions. But here I want to talk about this fully degenerate case, which is the case where it's not one-dimensional, the block of constraints. And an important tool for semi-definite programming and also for second-order con programming is the spectral decomposition. For SDP, it's the usual spectral decomposition which we use, but for second-order con programming, it's this one. So in fact, you can think of an SOCP as a two-dimensional problem, because every vector can be decomposed as a sum of two eigenvectors and eigenvalues. And the interesting thing about dealing with these conic problems is that you have a closed formula for the eigenvalues. It's simply this computation and this, and the eigenvectors are also clearly defined by these formulas. The hard case is at 0, which is exactly our case. Remember, we are at g of x bar equal to 0. But here you have the eigenvalues are non-simple, so we have multiple definitions of eigenvectors. So for each of these vectors w with norm equal to 1, you can get a basis of eigenvectors for this kind of thing. And for many properties that holds for usual eigenvalues of matrix, holds for eigenvalues of SOCP problems. For instance, a vector belongs to the con if and only if both eigenvalues are non-negative, which is the same as when symmetric matrix and positive semi-definiteness. And when you have inner product, a complementarity constraint, with feasibility, primal and dual feasibility, this implies that G and mu are simultaneously diagonalizable. This is the same as SDP. So we will use these tools. There's a picture here explaining the second order cone and all these properties. So see here, you have a vector Z, and the spectral decomposition is these vectors E1 and E2. You can see that it belongs to the cone if and only if Z is a linear combination with non-negative scalars. So you can see this. Also, if Z is on the boundary of the cone and it's orthogonal to some other vector, the other vector must be the other eigenvector in the other state. Let's say if you get E1 here and you ask which is the vector orthogonal to this one inside the cone, it will be E2. So they will share the same set of eigenvectors. Okay, so the idea is to, when we are looking at the KKT condition where this type of thing appears, we want to replace mu by its spectral decomposition. So we write it as lambda1 E1 plus lambda2 E2. And then what plays the role of the gradients of the constraints are these vectors here. You don't need to consider all m vectors, you consider only these two vectors. Actually, we want to make a change here. It's not the eigenvector of mu, but the eigenvector of g of x, which this comes from this simultaneously diagonalization. In fact, this is the correct vectors, which are the analogous of the gradients of the constraints. So since we were looking at constant rank condition, it makes sense because for linear problems, the Jacobian does not change, but the eigenvectors change with x. So it makes sense to talk about rank of these vectors for these conic problems. So our idea is that, well, if the constant rank condition will be defined in terms of these two vectors, what about non-degeneracy condition? Non-degeneracy should be also, we should be able to talk about non-degeneracy in terms of these two vectors. And then we get this easy linear algebra result. So we have that the m gradients are linearly independent if and only if these two vectors are linearly independent. And here, this is exactly the eigenvectors for the case of g equal to 0. So we have a basis of eigenvectors, and we apply the Jacobian to this basis of eigenvectors, and this is the set which must remain linearly independent. So how do you recast the linearly independence of m vectors in terms of the linear independence of two vectors? You do this by asking that this linear independence must hold for all bases W, for all bases of eigenvectors. Remember that in the case 0, you have multiple eigenvectors. And this also makes sense when you are not at 0. I won't mention this, but this is consistent with the definition of non-degeneracy when the constraint is not at 0. And it's also consistent with nonlinear programming. You can see nonlinear programming problems. You can define eigenvalues and eigenvectors for a nonlinear programming problem. And this is as when you see a nonlinear programming problem as a symmetric cone problem. Bruno will give a talk today about this topic, and he will explain the spectral decomposition in this more general setting of symmetric cones, which includes also nonlinear programming. But so this is just to say that this is all consistent with nonlinear programming and the other variants of the nondegeneracy condition. Okay, so for SDP, we have similar characterization. But here first, we need to rewrite the non-degeneracy condition by changing the basis. Since we are at 0, actually we can do this type of things here. You can rewrite your constraint multiplying by a basis matrix E. So E is an orthogonal matrix. Each column is an orthonormal. And so if the previous definition was when E was equal to the identity. So these Vij's In this case, Vij is simply the gradient of the constraints of each entry. But in general, you can write this condition on degeneracy in terms of this basis matrix E. And this is a characterization done by Shapiro, where you talk about linearly independence of these vectors Vij. And this is independent of the choice of basis matrix. If it holds for the identity, it will also hold for any other matrix. So how is our theorem in this case? It's this one. So non-degeneracy is that these vectors Vij's are linearly independent for some basis. So here we have our large set of vectors, m times m plus 1 over 2. So this set of m squared roughly vectors, they are linearly independent if and only if this smaller set of vectors, the VII's, which are m vectors, are linearly independent. But for this equivalence to hold, we must ask this for all basis matrix E. So this is a new view for this well-known non-degeneracy condition. It's a new characterization. Okay, but what is this useful for? So just a remark, if we have G not at 0, we have to consider a smaller set of vectors here, E1 to EP, which is the basis of the kernel of G. There is, you look at the eigenvalues, which are 0, and you compute a basis of eigenvectors. This is, but I'm not, I won't talk about this. But I want to talk about our main result, which is that we discovered that we don't need to consider all bases for this condition to be a constraint qualification. Non-degeneracy asks that for all bases, these vectors are linearly independent, and we show that we will show that we can remove some of these bases for the definition, and it will still be a constraint qualification. And with this, we make our peace with the diagonal case. So how do we do this? We do this in terms of this theory of sequential optimality condition. So in our group in São Paulo and in Campinas, we have been developing these tools for nonlinear programming in the past 10 years, and it has been a somewhat successful field. And the results are as follows. You have a local minimizer, and without any constraint qualification, we can show the existence of a sequence xk converging to x bar. So it's a perturbation of the solution, and a sequence of approximate multipliers, positive semidefinite matrices, such that the gradient of the Lagrangian converges to 0 at this sequence. So for this, you don't need any constraint qualification. And this has had many consequences, and many new constraint qualification has been defined using this condition. And the main thing about this condition is that you can use this to prove global convergence of some well-known algorithms. So many primal dual algorithms will generate this sequence xk and omega k with this property. So then we can refine its theory of global convergence. About complementarity, we can measure complementarity in many ways. But for us, we will stick with this second case. And because it says nothing, because g of x bar is equal to 0, so all eigenvalues are 0. So this complementarity says nothing, so we don't need to bother. What we need is to use this specific sequence of multipliers, which is defined here, because then omega k and g of xk will be simultaneously diagonalizable. Okay. So this is the full proof that this new condition is a constraint qualification. I won't go into the details, but you can read it for yourself and you can check that it's true. It's very easy. The idea is that you get this type of sequence, this sequential optimality condition. You have a minimizer, you build this sequence such that this converges to 0. And then you consider a diagonalization of this matrix omega k, which is this basis ek, which diagonalizes omega k and g of xk also. Remember, they are simultaneously diagonalizable. And then you assume that these scalars here, that the multipliers are unbounded. If they were bounded, you could simply take limits and you would get kkt. So there's nothing to prove. So if it's unbounded, then you can do some easy tricks here, and you arrive at a linearly dependent set. So you get, taking the limit, you have that this ek converges to some basis e bar, and this vector is linearly dependent. So this contradicts the non-degeneracy condition. So this is a proof that nondegeneracy is a constraint qualification using these two of sequential optimality condition. But here we can see that the only relevant bases, it's not all bases that are relevant, only the bases that can be attained by limits of bases of eigenvectors of g of xk. So these are what we call sequentially continuous bases, the bases that are limit of bases of eigenvectors of g of xk. Okay, so this is our definition of weak non-degeneracy. It's for every sequence xk converged to x bar, we can make a choice ek of an eigenvector basis of g of xk, such that you take a limit in a subsequence, and then these vectors are linearly independent, only for this choice of sequences, of bases. So let's see this in an example. So you have here a linear SDP problem, 2 by 2 constraint. Non-degeneracy would ask that these gradients would be linearly independent, which is not the case. So it's 1, 0, 0, 1, and 1, 0. So it's not, non-degeneracy does not hold for this problem. But weak non-degeneracy holds, because here you can diagonalize this matrix G of xy with the same eigenvector basis. You can choose this basis -1, 1, and this basis 1, 1. And so the only continuous basis is this basis of -1, 1, and 1, and 1. And when you compute the derivatives, you get a linearly independent set of vectors. So this is the condition holds here. The diagonal case. In the diagonal case, you simply choose the diagonalization equal to the identity. So the limit is also the identity. It's the only continuous basis. And then when you compute the derivatives, it's simply the gradient. So the weak non-degeneracy is the same as LICQ when you put it in the diagonal. Okay. Another example here for second order cone. So this is a linear problem without a KKT multiplier. So this is a problem with a duality gap. So the constraint here is this three-dimensional second order cone. Remember, the constraint is that the first component is larger than or equal to the norm of the remaining components. And here you can see that there is no Lagrange multiplier. It's simple to check this. Remember, the Lagrange multiplier must also be in the cone. So this vector must be in the second order cone, and then it does not hold here. But remember, we had closed formulas for the eigenvectors, E1 and E2, which were simply these things here. And the basis of eigenvectors were this type of vector, 1 W, 1 minus W, for W's with norm equal to 1. And you can see that you can reach any basis, W, by choosing the sequence xk, yk. This sequence xk, yk will converge to any W that you choose. So every basis will be continuous here. So, our condition is the same as non-degenerate for this case, and it also does not hold. But you can see which is the basis which is making the condition to fail. You choose this sequence, 1k and 0, and then this E2k will converge to this vector, 1 minus 1 and 0. And then when you compute the derivative evaluated at this vector, you get 0, and then the basis is linearly dependent. Okay, so we have also made some other extensions for, so this is using the idea of linearly independence. we get this weak notion of non-degeneracy. But we can also get a notion of weak Robinson, simply replacing linearly independence by positive linear independence. So we get also a new condition here, a weak version of Robinson. We can talk about constant rank condition by saying, instead of asking full rank of this set of vectors, we allow it to be linearly dependent, but they must remain linearly dependent in a neighborhood. Or you can talk about positive linear dependence, which is known as the CPLD constraint qualification in nonlinear programming. So all these extensions we can do to conic context. I think I'll skip this and I'll get to my conclusions. So previous definitions of constant rank conditions, they consider only the case where the zero eigenvalue is simple. There is only one eigenvalue which is equal to zero, which is what I call the one-dimensionality case. And here we have done this extension for the full general case. And this was done by characterizing non-degeneracy in terms of a linear independence of a smaller set of vectors, as long as we look at all bases of eigenvectors. And this makes sense for SDP, SOCP, and others. With this characterization, we show that only continuous bases are relevant. So we have this weaker version of non-degeneracy. And it includes the diagonal case, which is a relief for us from nonlinear programming. And the proof is based on sequential optimality condition, which is this well-known tool for nonlinear programming. We have defined this sparse version of non-degeneracy, which I didn't mention, and weaker versions of other constraint qualifications. And also with a small variation of this idea, we can define, we can prove the global convergence of an augmented Lagrangian method under all these new constraint qualifications. Okay, this is what I wanted to do. So I have some reference here. So the first two papers is the one that I'm talking about. It's not available yet, but it will be submitted soon. This is the naive case, which treats only the one-dimensional problem. It's quite an interesting paper. So if you are interested in this topic, you can check this. And this is the reference for the sequential optimality conditions for conic programming. There are several references for nonlinear programming, but for conic programming, so the first one is for SDP, and the second one is for second order con, and more generally for symmetric con programming. That's it. Thank you.
Thank you very much, Gabriel. Does anybody have any questions? I think we have enough people that if you have a question, you can just unmute and just ask your question. While we're waiting, then maybe I just have one question. You mentioned when you had this theorem, I think it was about slide 9, that you could use this to prove global convergence of some primal dual methods. Is that what you're referring to in the last item on the conclusion slide? Is that...
Yeah, exactly this. Yeah.
Okay.
So usually we use we do this type of proofs for the augmented Lagrangian method, primal dual augmented Lagrangian, and because it easily generates this type of sequence. So you see that the proof is simply saying that this type of sequence gets a KKT point under this new assumption. So you get the proof of global convergence for free. You don't have to do anything else. The algorithm, you simply need to show that the algorithm generates this type of sequential optimality condition, and you get the global convergence for free.
Okay. But so far, it's really only the augmented Lagrangian sub-method that you've been able to use it for, or are there other
No, we have done for nonlinear programming. We have analyzed interior point methods and SQP methods and some other methods. It's not all methods, because there are many different sequential optimality conditions, and some are easily generated by several methods, and some are more specific to interior point and augmented Lagrangian method. But at least the simpler sequential optimality condition, we expect that many methods will generate this type of sequence.
Okay, thanks. Maybe we have time for one more quick question.
Can I ask a question? So when KKT multiply, first, thanks for the very interesting presentation. When KKT multipliers do exist, what are the consequences of having weak non-degeneracy? Can you say something about the set of KKT multipliers?
You mean uniqueness or stuff like that?
Well, yeah, something like that. But I guess uniqueness shouldn't hold, I guess.
Yeah.
Right? But yeah, what can you? Did you find anything interesting you can say about that set?
Yeah, not yet. So we simply use this to show the global convergence of the augmented Lagrangian method, but we didn't have much time to look at more constants. It's kind of hard to work with this condition, but so we haven't found any new results about this. Only that it is a new CQ, and it gets global conversion of the augmented Lagrange. That's all the results that we have.
Okay, thank you.
Okay, thanks very much again, Gabriel.